Hi all. Last day we have discussed in a vector space V. If we collect an element alpha from V, then corresponding to different bases B and B prime of V, we can define coordinates of the single alpha relative to B and B prime. Today we discuss what is the relation between these two coordinates, alpha relative to the basis b and the coordinate of alpha relative to the basis b prime. We will prove that this can be related using a unique non-singular matrix P such that this coordinates of alpha relative to the basis B can be obtained by multiplying the coordinates of alpha relative to B prime with a non-singular unique non-singular matrix P. That means this P depends only on this B and B prime that never depends on this alpha and any other quantity. That means this will be true for all alpha belongs to V. This P remains constant for this alpha. So in order to prove that, we assume beta is equal to B is equal to alpha 1, alpha 2, etc. Alpha n is a basis for V, and B prime is another set of bases, alpha 1 except alpha 1 prime, alpha 2 prime, etc. alpha n prime. Now, if this alpha is an element of V, this alpha can be written as x1 alpha 1 plus x2 alpha 2 plus etc. xn alpha n. Any element of V can be written as a linear combination of elements of the basis vectors. So, if this happens, then alpha 1 prime can also be written as some p11 alpha 1 plus p21 alpha 2 plus etc. p uh, m1 n1 alpha n. Okay, so in general alpha 2 prime can also be written as p 1 2 alpha 1 plus p22 alpha 2 plus etc. p n2 alpha n. Similarly, each element of this alpha n prime can also be written as a linear combination of elements of alpha 1 alpha 2 etc. Elements alpha 1 alpha 2 etc. alpha n. That means these are all elements of V. So this happens for all alpha n prime or alpha 1 prime, alpha 2 prime, etc. So this is p1n alpha 1, p2n alpha 2 plus etc. pnn alpha n. Yeah. So I named these coefficients as Pij because these will be the candidates for constructing this P. Okay, so we can say that as far as this B and B prime are concerned, this Pij is constant. Okay, so this never changes. This Pij changes only when these alpha i's and alpha I primes are changed. Now we consider any alpha, then alpha can be written as, since this is also basis, this alpha can be written as some x1 prime alpha 1 prime plus x2 prime alpha 2 prime etc. xn prime alpha n prime. From this you can say that the coordinates of alpha relative to the basis b is the column vector x1, x2, etc. xn. Similarly, from this you can say that this implies the coordinate of alpha relative to b prime is x1 prime, etc. xn prime. Okay, but we know that this coordinates components of this coordinates is also unique for any alpha if you fix an ordered basis b prime. So our assumption is b and b prime are two distinct uh, ordered basis for this vector space V. Okay. Now we replace this is equal to this x1 prime can also be written, x1 prime times this alpha 1 prime can be written as this combination. So we can write it as p11 alpha 1 plus p21 alpha 2 plus etc. pn1 alpha n plus x2 prime times, next we have alpha 2 prime. Alpha 2 prime is nothing but p12 alpha 1 etc. So p12 alpha 1 plus etc. pn2 alpha n plus etc. The last one xn prime times alpha n prime is p1n alpha 1 plus etc. pnn alpha n. Now we will write this as a linear, this as a combination of alpha 1 alpha 2 etc alpha n. Now we collect all the terms of alpha 1 first, that is x1 prime p11, okay, that is from this one, and from this you can write it as x2 prime p12 plus etc xn prime p1n. That will be the coefficient of alpha 1 from this, plus the next will be the coefficient of next we will collect the coefficient of alpha 2. From the first term we can get x1 prime p21, x1 prime p21 plus etc. From the last you can get xn prime the second term, that will be p2n times alpha 2, okay, etc. What will be the last one? The last coefficient must be the coefficient of alpha n must be x1 prime pn1, x1 prime pn1 plus x2 prime pn2 plus etc. xn prime pnn. This will be the coefficient of alpha n. So we can say that now we write alpha as a linear combination of this alpha 1 this times alpha 2 plus etc alpha n. But we know that the coordinate of alpha corresponding to relative to the basis b is x1, x2, xn. Okay, but here we have the coefficient of the same alpha corresponding to the same basis alpha 1, base elements alpha 1, alpha 2, etc. alpha n. So we can use the uniqueness of this coordinates. Since the coordinates of this alpha relative to the basis b is unique, you can equate this x1 should be equal to this one, the first bracket, and x2 should be equal to the second bracket, and so on. So we will write the coordinate of alpha with respect to b as x1, x2, etc. xn. So this is equal to for the x1 we have the first term in the previous expression x1 prime p11, x2 prime p12, etc. x1 prime p11 plus x2 prime p12 plus etc. xn prime. We have this xn prime with p1n. So x1 xn prime with p1n. This will be the first term, and second term is from the previous expression. The second x2 will be equated to this x1 prime, again that is again x1 prime p21, x1 prime p21 plus x2 prime p22 plus etc. xn prime p2n. Similarly, the last will be x1 prime pn1 plus x2 prime pn2 plus etc. The last term will be xn prime pnn. Now we rewrite the RHS, that is equal to this RHS as we decompose this column vector as two product of two different matrices. So from the right we have x1 prime, x2 prime, etc. xn prime. This will be the second matrix, and first matrix we have p11, p12, etc. p1n. Now when you multiply these two matrices, the first term will be the product of first row with first column. that is this column. So p11 x1 prime, p12 x2 prime, and so on. So that will be the first term, and the second term will be p21, second row will be p21, p22, etc., p2n, and the last row will be pn1, pn2, etc., pnn. This shows that when we consider this x1, x2, xn as the coordinates of alpha relative to the basis b, and we replace this by a matrix P, where P is the matrix Pij. Okay, so this will be P times the coordinate of alpha with respect to B prime, and this Pij is defined as x1. That is the each Pij can be defined in the relation or using the relation. I write this that as like it as each alpha j prime can be written as p 1 j alpha 1 plus p 2 j alpha 2 plus etc. p n j alpha n. This is the relation connecting this pij and alpha i's. So it remains only to prove that this P is invertible. That is the only thing. So we will prove that this P is invertible or non-singular. This is a n-by-n matrix, so it is enough to prove that this is a non-singular matrix, or determinant is non-zero. So this is proved using the idea of the system of linear equation. When you consider a system of linear equation, homogeneous linear equation, Ax equal to 0. So this system has always a trivial solution, so that's why this is called homogeneous system of equation. So the classification of the solution of this homogeneous system of equation says that whenever this determinant of the matrix A is not equal to 0, if and only if this x equal to 0, the only possible solution of this homogeneous system is this. Whenever the determinant of A is equal to 0, if and only if this system has infinitely many solutions. So x equal to 0 has infinitely many solutions. So using this, whenever you prove that the system has only trivial solution, we can say that the determinant of this matrix A is always non-zero. So when you consider the system Px prime is equal to x. Okay, so we will prove that whenever x equal to 0, this reduces to the homogeneous system. In that case, we will prove that x prime is equal to 0. Okay, that means whenever x prime equal to 0, then we can easily get this x equal to 0. So we will show that when x equal to 0, the only possible solution of Px prime equal to 0 is x prime is equal to 0. That means we prove that whenever Px prime is equal to 0 implies x prime is equal to 0. This shows that P is, or determinant of P is equal to a non-zero quantity. Consequently, P is invertible. This is the idea we need to use to prove this P is invertible. Okay, this is very trivial thing, because when we consider the system of homogeneous system of equation, P x prime is equal to x and x equal to 0. Whenever x equal to 0, we can say that these xi's are 0. x1 equal to x2 equal to etc. equal to xn is equal to 0. Okay, this shows that what is alpha? Alpha is defined as x1 alpha 1 plus etc. xn alpha n. So that implies each xi equal to 0 means alpha equal to 0. Clear? But alpha equal to 0 implies from the expression of alpha in terms of alpha j primes, we can write this as alpha is equal to x1 prime alpha 1 prime plus etc. xj prime alpha j prime is equal, sorry, alpha xn prime alpha n prime is equal to 0. So this implies whenever this combination is 0, we can get x1 prime equal to x2 prime is equal to xn prime equal to 0, because this alpha 1 prime, alpha 2 prime, etc. are another set of basis elements. So whenever that linear combination is 0, we use by using the linearly independence of this alpha j primes, we can say that these constants are 0 or coefficients are 0. This implies these coefficients constitute the x prime, so x prime is equal to 0. So whenever x equal to 0, we can easily say that x prime is equal to 0. Then we can say that this p has only px prime equal to 0 has only the trivial solution. Therefore, the determinant of p is non-zero. From that, you can conclude determinant of p is non-zero or p is invertible. From the expression of p, we can say that this is unique. This expression is unique, corresponding to as far as this alpha j and alpha j primes are concerned. Because whenever we write alpha j prime as a linear combination of alpha I, we can say that this pij, this p1j, p2j, each of these coefficients constitute the coordinates of this alpha j prime corresponding to the relative to the basis b. Therefore, these coordinates are unique. We can say that this pij's are unique as far as this two distinct bases are concerned. So this shows that whenever we write these two coordinates of a single element relative to two distinct bases, we can connect or we can translate the one coordinate to another using a matrix P. Okay, so this matrix is also called transition matrix. Transition, because this translates the coordinates of alpha corresponding to one basis to another basis. Okay, this is the idea here. As a consequence of this result, you can multiply both sides with the inverse of p, since p is invertible. So we can write this expression as whenever we write alpha relative to the basis b prime is same as p inverse times coordinate of alpha with respect to relative to b. So this is what we call theorem 7 in our textbook. So any coordinates, any two coordinates of a same vector alpha relative to two distinct bases b and b prime can be related using non-singular matrix P.